Hey class, let's try another video solution. And I've gotten some questions on 28, and I think I see why. One, it's just a hard problem. But two, I think the author has done the solutions wrong. I think they were a little careless on something. Let me kind of verify that and run through this again, because I had a student ask a question, and I was like, I think something's missing here. And so when I flipped over to the author's solution, I said, yeah, this doesn't look quite right. So let me run through it in my own mind, and then I'll look up here at the author's solution, and I don't see two parts to his energy equation. That's bothering me. So here's what we have here. The problem says a ball has an initial velocity of 8 meters per second, and it rolls up a hill without slipping. Okay, so I'll draw a little ball here. Maybe I'll draw the ground, and then I'll say it goes up the hill. And so it'll roll, and eventually come to a stop at some height h. And that's the question. Treating the ball as a spherical shell. So in other words, it has mass just on the outside. So maybe this is like a tennis ball or a racquetball or a basketball, but its center part is nothing's in it. It's an air core, if you will. And that's important. And I'll just put here the eye of a shell is 2/3 mr squared. You see, if it was solid, like we did the Earth being solid back on number 16, we would do a 2/5. But this is 2/3 because, again, the mass is further out. And so it's a bigger moment of inertia. All right, so I got that from the table there. Okay, now it says calculate the vertical height that it reaches. So using the principle of conservation of energy, and so let me pause right there and make my normal statement that what you want to do in these problems is to do the same principles that we did for translational motion that we do for rotational motion. And that's kind of an important piece to this puzzle here. All right. Now, if I had a ball that I said, okay, I'm just going to throw it up and see how high it goes, I would use the principle of conservation of energy. And so I'm going to do the same thing, although this time it's going to be a ball rolling up a hill. And here's what I'm getting at. I got to start by adding up all the energies. And before we got into this chapter, we said the kinetic energy plus the potential energies. Remember, there was one for gravity, and there was also one for a spring. And then the work done by the non-conservative force, like friction. All of those added together would equal to the final kinetic energy plus the final potential energy. So maybe I should put initial, final, and final. And what I added here in this problem, or in chapter 10, was to say, not only is there two types of potential energy, but there's two types of kinetic. There is a translation and a rotation. And that's what's going to elevate this problem from chapter 7 to this chapter, chapter 10. We will have one more term of energy. Okay, and so I would say that down here at the bottom, it has a translational kinetic energy, and it also has a rotational kinetic energy. And so this object, this ball, is both translating and rotating. Now, down at the bottom, it has zero potential energy, and you might even say zero from a spring. And it says without slipping, so there's no rubbing, no friction. And so the 3 zeros here represent, well, this last zero represents the friction due to sliding, kinetic friction, there isn't any. This one represents the potential energy due to a stretching of a spring, and that's going on. And this represents the gravitational potential energy, and that one I'm going to call 0 because I'm going to call down here at the bottom of the hill y equals to 0, and so it is going to go up the hill. I guess all of that is a nice way of saying that over here on the left-hand side, I have an object at the bottom of the hill, and looking at its total energy, I would say I need two pieces. One is its translational energy and one is its rotation. And by the way, that's what's bothering me here about this solution. I'm looking at this going, I think the author only did this. The author got careless and didn't do the fact that a ball would be translating as well as rotating. Okay, so I'm going to keep going because I think it needs both of these terms. The ball, it would be both translating and rotating. Now, the other side of the equation right here, the final energy, would be the final kinetic energy at the top. Now, since they said it comes to a stop, I'm going to put 0, but I'm going to put 0 twice. Well, the first 0 is what is its translational kinetic energy, and the second 0 is what is its rotational kinetic energy, to show you I'm thinking about all the energies. And, of course, they're both 0, came to a stop. All right? Now, when I talk about the potential energies, there would be this mgh. That would be the gravitational potential energy. And then I'll put a 0 for completeness, but this would be the energy from the spring. And again, there is no spring, so that's kind of silly. So I've got a bunch of them that are zeros, and our energies always come out that way. But it looks like what it boils down to is the two kinetic energies at the bottom of the hill then get transferred into gravitational potential energy to get it up to the top of the hill. And so now we can answer their question, how high will it go? Now, of course, to do this, I've got to take a little moment and think about how the angular speed and the translational speed are related. So let me leave the first term alone. And like I said, this is where I think your author has got it wrong. He's left this one off. He only has this one right here. And he puts in a correct moment of inertia, as we talked about, a shell. So that would be 2/3 mr squared. And then also the angular speed would be a v squared over an r squared, mgh. And looking carefully at this, you can see that the r squareds cancel off. So it doesn't matter what the radius of the ball is. In fact, that was bothering me for a moment. I'm like, oh man, they don't say how big this ball is. They don't say whether it's a tennis ball or a racquetball or a basketball. Fortunately, those two work together and it doesn't matter. So the answer is going to be the same for a tennis ball, a racquetball, basketball, any hollow object. Okay. There's some other neat things that cancel off. Right away I see a 2 canceling off, but another big one is there's an m in every term. That cancels off. So if I simplify what I have so far, I have a 1/2 v squared here. It looks like I'm also left with a 1/3. That cancels v squared. And then a g, and then an h. And so I'll say it again. It looks like your author just has this term. He's got the 1/3, he's got the v squared, and he moves the g over, but he's making a mistake by missing that one. So, thank you for following along with me, but usually authors don't make mistakes, so usually I do. So I wanted to just kind of like, okay, you sure this is the author's mistake and not me? And yeah, that's what I'm thinking. Unless there was some other misinterpretation of the question, but I don't think so. So I'm gonna keep going with my approach here. Now maybe I'll get a common denominator of 6. Because a 1/2 would be 3/6, and a 1/3 would be 2/6. And so factoring out a v squared and getting a common denominator of 6 gives me 5/6 v squared equals g over h. So finally, I can now solve for h. It would be a 5/6, then the speed squared divided by g. So grabbing my calculator, I would take, I guess, 5/6 here. And the speed, what did it say, 8? So 8 squared. Then divide by g, which is 9.8. And this height would be 5.44 meters. And so, yes, that's a different answer than your author gets. Because, like I said, I think your author got careless and did not include that term. But a ball rolling has both translational and kinetic energy, which is why mine's so much higher, because I'm giving more credit, if you will, more energy to it. I'm giving it an energy of translation and rotation. Your author gets a height that's based upon just the energy of rotation, and it's not giving it any credit for having a translational kinetic energy. So, again, I think he's wrong, and I think it doesn't go high enough because he didn't include all the energies. Now, if you look at B, your author, I think, wants you to see that if you only included translation, so it says here, part B, repeat the calculation for a same ball that slides up the hill without rolling. Now, I think they also mean slides up without friction. Because if I apply the conservation of energy, in other words, this is a block instead of a ball, I would say that the block will not go as high because the block doesn't have as much energy. The block has energy only of translation and nothing for rotation. And because it has less energy to start with, it's going to go to a smaller height in terms of potential energy. Now, you might argue that it would go even lower if some of this translational kinetic energy shows up as heat energy. Then it would even go less of a height. But I think because your author doesn't give you anything like a coefficient of friction, doesn't talk about the friction, so the author could do a better job on this problem and say, block sliding up without friction. And you'll see that it just doesn't go as high because it doesn't have as much energy. And if you included friction, it would be even a second reason it doesn't go nearly this high. But we can't really include friction in this problem because we're not given information about it. So I think the author is just trying to point out that it won't go nearly as high because we don't have nearly as much energy because we're missing the rotational energy that a ball has. A ball has both translational and rotation, where a block does not. So the second part really is a throwback to our translational one, not our new stuff. So I'll just go 1/2 mv squared for the initial energy just has to equal the mgh. And so that would be kind of this step right here where I'd say don't let it rotate. It has no rotational kinetic energy. And so if that's the case, then I can then cancel an m and move the g to the other side, and I will get a height. That notice when it was rolling, I had a 5/6. But now I have a 1/2, which is why it won't be as big as a number. So let me go 1 divided by 2 for the 1/2. Let me go 8 squared for the speed squared. Let me go divided by 9.8. And I get 3.26 meters. And then looking at your author's solution, we agree here on part B. Your author just gave it translational energy, and that's what I think the author wanted here in B. But like I said, A can be a little confusing for you, because I think the author really should include both, and I didn't, and I think that's why I'm getting a lot of questions on it. So hopefully my little video helps. All right, take care.